Hello. We're going to be using this YouTube again. I had actually made you an overview the last couple of days, and this is literally the third time I've made this. So I'm going to be going over just examining the hemodialysis system very quickly within the next 15 minutes. As you can see here, here's the dialysis machine. This right here is going to be the bicarbonate that you'll learn about. These lines are hooked up to the patient. There's going to be an arterial line that's going to take the dirty blood from the patient, and then also a blue venous line that's going to push the clean blood back to the patient. The dialyzer's right here, you can hardly see it, but that's going to be the artificial kidney, and we'll talk more about that. Different components of the hemodialysis system. You've got the water treatment system. This is going to be very pure, not sterile water. It's used in conjunction with the dialysate and as well as the bicarbonate. And you're going to learn more about this in the upcoming learning plans. But really it's must be processed to remove any impurities in this water. A dialysis patient is exposed to a ton more water than any normal person would be, and that is why it needs to be extra pure. The venous access is also needed. Like I mentioned, there's going to be 2 needles typically placed if there's an arteriovenous fistula or graft. So it could be natural or synthetic. That the one with the needles is going to be an internal access. It's going to be placed in maybe the arm, forearm, upper arm, and sometimes occasionally a graft may be placed into the thigh. The external would then be a catheter. And this would be used in the same process, but needles wouldn't be needed. And hopefully this would be used for temporary use. And you'll learn more about that too. This is a picture of a dialyzer. It is the artificial kidney. This is what's going to be removing the most of the excess fluid waste and also maintain the electrolytes and control the body pH. A downfall of this is that it's unable to produce hormones that the kidney would typically make. Then this jug here is going to be the dialysate, also known as the acid or bath. All 3 names are used interchangeably. They all mean the same thing in dialysis. So dialysate is going to be on one side of the dialyzer, while the blood is going to be on the other. Inside the dialyzer is going to be tiny little pores, fibrous, hair-like structures. There is actually probably about 1 million or so of them within the dialyzer container itself. Blood is going to go on the inside, dialysate is going to flow on the opposite side. And this is going to assist in moving waste and a surplus of electrolytes from the blood. It's going to replace substances such as calcium bicarbonate that the patient will need. So this here, waste and fluids are removed by which blood, from the blood by which principle. You're going to be learning about this in the next learning plan. Diffusion. So diffusion is the movement of solutes through a semipermeable membrane from a greater to lesser concentration until both sides of the membrane have equal concentrations. Much like squirting an aerosol in the air, you have lots of particles that start out in one area, then they gradually go into the rest of the room, so the entire room will smell like whatever you had sprayed. That is one visual of diffusion. Next, we're talking about the dialyzer itself, and due to time constraints, I'm just going to go through it kind of quickly. So we're going to be learning about how they work, different advantages and disadvantages of these different types of dialyzers, as well as the characteristics that you're going to need to know about. So the design of the dialyzer. Hollow fibers are the only type of dialyzers used in facilities today. At the end of each dialyzer is going to be a potting material. The purpose of this is going to just to hold open those little fibers that the blood will go through. Blood is going to enter from the top of the dialyzer and then exit from the bottom. The dialysate will then go the opposite direction, bottom to the top. Blood and dialysate must never mix. This may happen if the membrane breaks. That's why I mentioned that the dialyzer should never be dropped or shaken. Those membranes could break and then blood and dialysate would mix, causing something called hemolysis, which would then excrete different potassium, which could be extremely harmful to the patient. So you'll want to remember this. And then finally, that blood and dialysate flow is actually in a countercurrent flow. So the dialysate will flow in the opposite direction of the blood, and that's going to increase diffusion. So some advantages. There's many different tiny fibers within the dialyzer, so that helps. That's definitely an advantage. And through this, ultrafiltration is well controlled. Disadvantages would be that there's lots of air present in the dialyzer and needs to be removed. We'll learn about how to get that out. Some of them will use a certain type of chemical that can produce adverse reactions. And there is, because it's not made out of a body composition, close to it, but sometimes not enough, more heparin will be needed to be used. These are the different ways that the dialyzers will be sterilized, and you can look at those. Different categories, there's conventional, high efficiency, and high flux dialyzer. Only thing different between these is that they are going to remove larger or smaller types of molecules. Membrane materials, it's selective permeable, like I mentioned. So some solutes are going to be able to pass and others will not. Bigger molecules are going to be kept in, while the smaller ones are going to be excreted into the discard material that will go down the drain. Different characteristics, importantly, biocompatibility. So how well does the dialyzer function with the body? Does it produce an immune response? How similar is it to the human body? We want to make sure that the body can tolerate this type of dialyzer. Surface area is important to know. It's the size of the membrane, how well the dialyzer removes solutes. More surface area, so bigger the area, more exposure to blood and dialysate, which means more solute removal. Molecular weight, this is just going to refer to how large the size of the solute can pass through the membrane. So larger molecules have larger molecular weights. Membranes are chosen on what type of molecules can be removed. So a larger dialyzer, more than likely, will have larger surface area and will be able to remove more molecules than that of a smaller one. You can take a look at these here, and just to know what all of those mean. Clearance is important. How well solutes are removed from the blood. We'll talk about clearance quite often in a facility. It's how well is that patient getting dialysis? Are we cleaning them well? Is their blood being cleaned well enough? Or do we need to do something to change that? Here we go with effectiveness, same type of thing about the clearance. So this is a blood test that we actually do to check how well the dialyzer will work. Will depend on the surface area, also how fast the blood flow is going and how fast the dialysate will go. These are the different types of synthetic materials needed that the dialyzers are made out of. These are the 3 ways to remove solutes. You'll want to take a look at these because these will be important this chapter as well as in the next learning plan. So diffusion, majority of solutes are removed by diffusion in dialysis. This is going to be the best way to remove the small solutes. Convection, also called solvent drag. This will also assist in moving the large molecules. So the big guys are going to follow the small guys. And then absorption, when proteins stick to the membrane. Synthetic membranes will absorb more than cellulose membranes. Dialyzer absorption depends on the makeup of the membrane. Okay, and you can take a look at this question on your own time. So there are delivery systems. This is going to prepare and deliver the dialysate to the dialyzer. Some units supply dialysate for a single patient, like in that jug at the very beginning of this presentation. Other units are able to supply to multiple dialyzer stations at the same time. And that's going to be called something on the wall. We'll say the dialysate's on the wall. So what that is, here we can see it right here. They're going to have large mixing tanks in the back in a separate room, which will hold either acid or bicarbonate or both, and then be transferred to all these other tanks that will then be fed through different pipes that gradually go through to the machine. So it's kind of a nice process. You're just turning a dial rather than using a wand and putting it into a jug. This is a very important slide. Dialysate and its purpose. I mentioned that it's also known as bath or acid. A lot of times I'll probably say acid just because we always call it that. Dialysate is remember that it's one side of the dialyzer membrane and blood is going to be on the other. It assists greatly in removing waste and a surplus of electrolytes in the blood, replaces substances such as calcium and bicarbonate that the patient needs, and also keeps the pH in balance. Wastes are removed while needed solutes will stay. Again, blood and dialysate must never mix. These are the different components in dialysate. So it's basically what you'd think when I say acid. It's going to be the acidic portion of the dialysate. Then there's also the bicarbonate, which is typically something that's going to be separate from the acid. The two are needed to kind of neutralize the blood to make it consistent of what the blood and the body needs. You can look through different sodium, potassium, magnesium, calcium, glucose, and then bicarbonate and citrate, and just kind of get an idea about these different things and what they're talking about here. You'll want to kind of focus on the sodium modeling. It's not really used in facilities a whole lot anymore. Sodium and water kind of go hand in hand. And sometimes people have a hard time removing extra fluid that's needed to be taken off. So what they do is they increase their sodium level. By doing that, they're able to remove more fluid because the blood pressure will increase. So risks of doing this are going to cause weight gain, thirst, and even elevated blood pressures. So like I mentioned, a lot of facilities aren't doing this anymore. Important to know, flow of dialysate. So dialysate flows through the dialyzer at a prescribed rate. It's going to flow in this countercurrent flow. So if you think of countercurrent as opposite, blood flows one way and dialysate flows the other. Blood and dialysate flowing the same direction would be called concurrent. So that would be the same. We use countercurrent. So remember that. Verifying dialysate is an extremely important task that we will all learn to do well. It is in the patient's best interest to make sure that this is verified. If not, this dialysate contains a lot of electrolytes that can be very sensitive to the patient, such as potassium. Too much potassium, too little potassium could potentially kill that person. So we need to verify making sure that it's accurate when that person is hooked up to that type of dialysate. There's different accessory equipment. A lot of safety devices. You have the blood tubing, which is shown here. Blood pump is going to move the blood through this extracorporeal system. The speed is controlled by staff. There's also a heparin pump infusion. This is going to deliver heparin, which is an anticoagulant, the way to thin the blood. It also helps to prevent the system from clotting. I'm going to have you take a peek at all of these. These are just different things that the machine is going to be kind of doing that you're not even going to know it, basically. So conductivity and what that is. It's to measure conductivity, which is going to be pretty much the measurement of all of the electrolytes that are in the dialysate. There's a handheld machine called a Phoenix meter that's used. That's going to tell whether or not it's between a certain range and if that's an acceptable range or not. The pH will also be used with this conductivity meter. They both work together, and you'll also verify that with the machine itself. So take a look at all of those. And that's pretty much the end. I apologize for it being so brief. I will post this video as well as if my Collaborate ever pops up. Like I said, I recorded it the other day, and I don't know if it takes 24 hours or what it is. Make sure that you do your study guide. That's going to greatly help you. Remember that I'm here if you have any questions whatsoever to answer, and feel free to stop by the lab. Let me know and we can take a look around. Thanks, and have a great day.